So the first time I had the pleasure of reading some of the works of Roger Blandford, I was a grad student, and I had this pile of papers and articles trying to get up to speed on relativistic jets from black holes. These are spectacularly powerful phenomena that I don't know if he's going to talk about it, but he's one of the top researchers anyway. And one of the piles was how can a jet be produced? And there's this theory number one, scenario number one, Roger Blandford et al. Theory number two, another possibility, Blandford and co-author. Third possibility, Roger Blandford and someone else. And it was like, this man is a genius. If nature decides to use one of these processes, he got it covered. And as a byproduct, of course, whatever the outcome, the jet will be called the Blandford jet. That's for sure. To do this, you have to have three main qualities. One is curiosity, of course. The second one is deep knowledge. And the third one is imagination. And thanks to these qualities, he managed to give key contributions to a number of fields in astronomy. One is, of course, black hole and general relativity. The other one is particle astrophysics, and then there's cosmology. He started in Cambridge with Martin Rees, and then he stayed in Cambridge again for a postdoc. Then he moved to the US, Princeton, and then he moved to California to stay there, and I know why. So there was Berkeley first, then Caltech for almost 30 years, 27 years, and then he was appointed director of the Kavli Institute for Particle Astrophysics and Cosmology that they just built. Some says built around you, but I'm not. I'm not saying that here. Well, I do. And where he actually oversaw the research for 10 years until 2013 of one of the world's top institutes seeking answers to some of the great cosmos questions, such as what powered the Big Bang, or what are dark energy, dark matter, and what happens around black holes. So it's a real pleasure to have him here. He will talk about gamma rays, cosmic rays, and neutron stars and black holes for us. And thank you, the BBVA Foundation, for inviting him.
Well, thank you very much, Simon, and thank you very much, the BBVA Foundation, for your kind invitation to come here, and thank you very much for coming to listen. And I'm very excited to be here and tell you about gamma rays and cosmic rays and neutron stars and black holes. So roughly 6,000 years ago, a 961-year-old neutron star, which we also call a pulsar, it's about the size of Madrid, but it's as big as a star, and it spins on its axis 30 times a second, and it has a very strong magnetic field. And it used this to accelerate a charged particle called an electron to create an uncharged particle of light, which we call a gamma ray photon. And this photon made its way out of a dense crowd of other photons and particles, all eager to make its acquaintance, and it escaped the expanding debris of the supernova explosion that created that neutron star, which we call, and now a famous object to astronomers, the Crab Nebula. And this photon made its way into the dark space between the stars and crossed the galaxy. It's now inside the solar system, within the orbit of Jupiter, and by the end of this lecture, it will make an appointment with Fermi Gamma Ray Space Telescope here, and it will interact with the nucleus of tungsten and create an electron and a positron, and it'll signal on some wires, which will be transmitted to a station in Madrid, and then transmitted to the Stanford Linear Accelerator Center, where I work part-time. And there we will think about it. This photon that's come all the way from the far reaches of the galaxy in the Crab Nebula and the pulsar, which we can see there in the middle of just this tiny little pulsar about as big as Madrid inside the Crab Nebula there. And that's the Crab Nebula there. So, to tell you a little bit more about this story and about these electrons and photons, I'd like to start with Isaac Newton. And you can see a depiction, not a very good painting, of a famous event when he used a prism to split the light from the sun into its constituent colors. And he showed that there was many colors there, which we can see there, and you know this. And we think about this as physicists as just being essentially one octave of frequency. And it goes from the red, and beyond that the infrared, to the violet, and beyond that the ultraviolet. And if we just think about it as an analogy, it just corresponds to, say, one octave on the piano. Now, the frequencies involved are in the terahertz range. This is not showing up too well, this screen, but that's okay. Then the terahertz range, and that's about a million, or I should say 10 to the 12th, times the frequencies associated with the piano. But don't worry about that. Just think about it as one octave on the piano, the light that we can see with our eyes. In terms of wavelength, it's a wavelength slightly shorter than the wavelength of a micron, which is a millionth of a meter. Now, so that's tera means 10 to the 12th. So that's just one octave on the grand piano. Now, if we think about the electromagnetic spectrum, all of the waves that are like light that astronomers can explore, then in fact there are about 70 octaves of electromagnetic radiation that astronomers can look at. And so what we see with our eyes is really just that small single octave in the middle of all those grand pianos. So there's about 10 grand pianos worth. And if we try and think about the particles of light that are associated with those waves, then we call them photons, and they have energies, which I'm going to measure for a reason that will become obvious in units that physicists like to use, called electron volts, or EV for short. And I want you to get used to some big powers of 10 here. This is all, for many of you, will be quite new, but an electron volt is roughly the energy of a particle of visible light, a photon of visible light that you might be detecting with your eyes. And then 1,000 times that we will call a keV. And that will be 1,000 times the electron volt, and that's in the X-ray range. And then we go up to the MeV, which is 1,000 keV, or 1,000,000 electron volts. And then we go beyond that. And instead because there's a confusion about billions and so on in different languages, I'm going to use the notation of saying it is 10 to the 9th, which really means it is 1 with 9 zeros after it. And so there are 10 to the 9th electron volts in a GeV, and that's about the energy of a proton, the center of a hydrogen atom. And then, for the purposes of light, we go up, as astronomers, all the way up to 10 to the 12th electron volts, which I shall call a TeV. These are the standard physics and astronomy nomenclature for these photons. So as we go from the visible light all the way through the X-rays and the gamma rays, then we're going up to 10 to the 12th times the energy of a visible light photon in the largest gamma ray photon. And we observe those gamma ray photons in the GeV range from around about 10 to the 9th with the Fermi Gamma Ray Space Telescope, which is in orbit around the Earth. And then in the TeV range, we use a series of telescopes on the ground, of which one of the prime examples is a telescope called MAGIC, which is in the Canary Islands, which you should be very proud because it has made many wonderful discoveries. And the gamma ray astronomers, as you can see, have 4 grand pianos worth of energy in the photons to play with. So we're very pleased to have all that great opportunity. So before I say a little bit more about the context, I want to just do a little bit of physics. For many of you, this will be well known. For others, it will be something new. And so the first thing I want to say is you may have been slightly confused about me talking about waves of light in terms of particles. And really, there is a sort of duality here. And we can think about light, for some contexts, as being waves, like waves on the ocean. But we can also think about it as being particles, which we call photons. And it's a matter of convenience which description we use. They're equivalent. And it turns out that if we're looking at very low frequencies, the radio waves, which are right on the left-hand end of that series of grand pianos, then we think of them more as waves. And if we look at the right-hand end, the gamma rays, we tend to think about them as particles. So that's one thing I was going to get out of the way. And so if we think about them as particles, we might ask, well, how do we take a particle like an electron, which has a charge on it and it orbits a proton and a hydrogen atom, how do we make a photon? And the answer is we just shake it around a little bit. And so if we shake it around, we can do this using a magnetic field. This happens very commonly in astrophysics. The charged particle like electron is shaken around by the magnetic field, and that shakes the electric field around, and that electric field creates photons, and we call this synchrotron radiation. This is a very common thing to happen in astrophysics, and we know of many sources, including the Crab Nebula, which I've just shown you. And this is especially important when you're dealing with particles that are traveling with speeds very close to the speed of light, very energetic electrons, and we call those relativistic when they're moving with speeds close to the speed of light. And this is how those particles get that energy, those very high energies, is the problem I'm going to be talking about today. This isn't the only way of getting photons. Another way is to have a collision when that electron crashes into a proton. There's a process that is known as Bremsstrahlung. That also will shake the electron up and make photons. And we also can have protons themselves can hit other protons, and they can create positrons and particles called pions and particles called neutrinos, which we know all about from the laboratory. And these two can, under appropriate circumstances, create gamma rays. Finally, there's one technique that is a little bit important for our story, and this is an analog of the sonic boom, which you may have heard from a supersonic aircraft or the shuttle or something like that. You can hear a sonic boom on the ground. The light analog of that is something that's called Cherenkov radiation, and this is in fact the principle that's used by the MAGIC and HESS telescopes to see the TeV gamma rays, because what happens is a very high energy gamma ray hits the atmosphere, makes lots of particles which travel faster than the speed of light in the Earth's atmosphere, and that makes Cherenkov radiation, which is a bit like a sonic boom. And that's how those particles are seen. So let's go back to our pianos. We don't just have light particles called photons. we also have cosmic rays. And the cosmic rays nowadays refer to the charged particles which come from outside the solar system. They come from our galaxy. And we see them at Earth from all the way from the energies of MeV. Now, an MeV, you may recall, is 10 to the 6 electron volts. And now we're going up to even higher energies than the photons. We go to GeV, which is 10 to the 9th, TeV, which is 10 to the 12th, PeV, which is 10 to the 15th, EeV, which is 10 to the 18th, and we haven't quite yet detected a particle directly with 10 to the 21, which is a ZeV, but the particles that we do see were probably created with those energies at their sources. So we have enormously energetic particles, like a ZeV, and so let's just say a zeta electron volt, a ZeV, that's 10 to the 21 times the energy that's in a humble photon that we're seeing with our eyes. That is a truly remarkable thing to happen, and the challenge here is to explain how this does happen. If we look at it at the top of the atmosphere, we call these cosmic rays at the right-hand end of that list of grand pianos with energies up to the EV range. We call those ultra-high energy cosmic rays. And when one of those hits the atmosphere, it makes this, as you can see there schematically, a whole lot of charged particles called a shower, and that's what we can detect with these telescopes. That's what we can detect using special telescopes to look for those cosmic rays. So essentially we see flashes of light, and we can also see the individual particles themselves when they get, some of them when they get to the ground. So we can detect the cosmic rays as well as the high energy gamma rays. And just to give you this is the way it's detected, the highest energy cosmic rays. This is a postage stamp that commemorates a very successful cosmic ray observatory in Argentina. And that observatory, as I say, can look for these cosmic rays using the flashes of light that they create and also the particles that are seen on the ground. And just for comparison, here is a physics experiment that you may have heard about, a big physics facility called the Large Hadron Collider. And this accelerates protons to energies now of about 10 TeV. So 10 TeV right in the middle, we can see we're dealing with 10 to the 9th times those, 10 to the 8th or 10 to the 9th times those energies in nature. So this is the Large Hadron Collider in Switzerland. To give you an even more graphic example, you may recognize these gentlemen, and this is a penalty kick, and roughly speaking, the energy of the ball is about that of the highest energy cosmic ray, a subatomic particle. Now, for those of you who know physics, do not confuse energy with momentum. The goalkeeper is much more concerned about momentum than energy, and this particle, although it has the energy of a well-hit soccer ball or any other type of ball, it only has the momentum of a snail. So you can, that is a comparison. So, in fact, there's even more that we can explore, and that is, we've talked about the cosmic rays and the photons. In astrophysics, we can look at the neutrinos. We are detecting now neutrinos. These are these ghostly, weakly interacting particles, and I'll say a little bit more about that. We are seeking dark matter, but we haven't as yet got a positive detection. And we are, I think, on the threshold of detecting gravitational radiation at low frequencies. And all of these are important windows on the universe and part of the story that I'm going to try and tell you. So if this has been a little bit too much to hold, and you do know that there's an exam after this talk, so here's the range of energies here, and I've just summarized, and you can see the big range that we've got there, and they go from optical photons all the way to the highest energy particles that are accelerating. So if we now want to talk a little bit more about how we detect these particles, I'm not going to tell you about every observatory, but I'm going to tell you about some astronomical observatories that are important for my story. So firstly, the X-ray telescopes are important, and those have to orbit above the atmosphere. And here we have 3 X-ray telescopes out of many, but 3 very important ones. There's Chandra X-ray Observatory there, which is a US-led mission. There's the European-led XMM Newton mission. And then there's New Star, which is another international mission that goes into higher energy X-rays. And these are all telling us a lot about the sources of these high energy particles and high energy photons. Also new on the horizon are radio telescopes, and although radio waves are very low frequency and the radio photons, if you like, are very low energy, they are created by the same relativistic particles that make X-rays and gamma rays, and so they are a very large part of our story. Here's the completely rebuilt, very large array in New Mexico, 27 antennae that does superb observations. Here is a new joint project to do millimeter astronomy, not radio astronomy like the VLA, but this does shorter wavelength, millimeter astronomy. This is in San Pedro in northern Chile, and it's a joint operation now involving many countries, but led initially together by Europe and the United States, but also involving Japan and other countries, including, of course, Chile. Here is a Dutch low-frequency array, which is telling us a lot about these cosmic sources, and it's just coming online. And here is the future of radio astronomy, which is a project called the Square Kilometre Array. It's the Square Kilometre Array, and we hope that that will be built sometime, somewhere within a decade. We have other ways of learning about charged particles close to home. There are two satellites that have left or are leaving the solar system, passing through the outer parts of the solar wind and going out into the medium between the stars. These are the Voyager spacecraft, and there were two of them, and they were launched in 1977, and they are still transmitting data and telling us about the sort of physical processes that go on in cosmic environments. I mentioned neutrino astronomy. There is a new facility called IceCube at the South Pole, and there you look for little flashes of light, and in fact you can also use radio waves to detect the neutrinos. They're very weakly interacting particles, and they are starting to see neutrinos from what they believe to be astronomical sources. We have no idea yet what they are. We have many possibilities, but we haven't been able to identify them. There are about 40 or 50 that have been seen so far, but it looks like almost all of them come from the universe, and it's one of the great challenges to try and understand what processes and what sources there are for these. And then, as I mentioned, gravitational radiation. We're on the verge of seeing gravitational radiation, and these are waves of gravity, rather like the electromagnetic waves that are important for that are the photons that I told you about, but this is very low frequency, and these are general relativistic waves. They travel at the speed of light, and they're created by the same sorts of objects that are responsible for the highest energy particles. In particular, we have detected indirectly gravitational radiation from two neutron stars in orbit about each other, and we are seeking directly evidence of gravitational waves by actually seeing mirrors in a facility. Here's one here. It's essentially two mirrors that are shaken around by the gravitational radiation. It's a tiny, tiny motion that's being detected, and it's detected using powerful lasers. So we use these powerful lasers to detect the passing of gravitational waves. That hasn't happened as yet, but with the newly sensitive instruments called LIGO, Advanced LIGO, in the United States, and Virgo in Europe, with these new instruments, you are able to see passing gravitational waves, and we hope within a few years there will be positive detections of these, and we hope something that we didn't expect. Another technique for finding gravitational radiation that is also perhaps on the threshold of making a discovery, we don't know, is to use the same pulsars like the Crab Pulsar, but ones that spin even faster, and they are wonderful clocks, and by timing the pulses that come from these many wonderful clocks, you can also detect the passing of gravitational waves. And we hope to find detections that way. And then in the future, a European-led mission called LISA, we hope will, in about 10 or 15 years, will, we hope, be launched and produce the most sensitive detection of gravitational radiation. So let's go on to the cosmic rays and recapitulate where we are. I've drawn here a graph of the intensity of cosmic rays. On the left-hand side, you can see at the low energies, which I've started at about a GeV or thereabouts. That's about the energy of a proton, just to remind you. And I go all the way up to this famous Ronaldo penalty kick at around about the ZeV range. And you can see there are lots and lots of very low-energy cosmic rays, and there are very few very high-energy cosmic rays. But we have to understand the sources of all the cosmic rays over that very large range of energies. And we think that the lowest energy ones come from the Sun and Jupiter, and we can actually watch those processes in action. If you go a little bit higher, we believe that we see particle acceleration at the giant explosions that are created by supernovae, which mark the end of massive stars, the end of life of massive stars. They explode, they create giant expanding debris, which drives shock fronts into the interstellar medium, and we believe that those are responsible for particle acceleration. And I'll explain this in a short while. As we go on, there are the pulsars, like the one that's sitting in the middle of the Crab Nebula. We saw that picture there. So there's a pulsar in the middle of the Crab Nebula, and those are perhaps responsible for slightly more energetic particles. And then if we go to the very highest energies, we don't know that this is the case, but I'm going to explain to you a theory that the highest energy particles, in fact, come from large shock fronts associated with clusters of galaxies. So that's giving you some context. Now let's talk about how nature might actually perform these tricks and accelerate these particles to very, very high energies. The first mechanism I shall describe is it's one of basically two types of mechanism, which we believe is very important. It has the rather ponderous name of diffusive shock acceleration. And basically, the idea is that instead of the particles getting their energy just in one big, enormous acceleration event, which might happen, for example, at a particle accelerator, like the one that I work at SLAC, instead, they gain their energy systematically. Sometimes they gain energy, sometimes they lose energy. Typically, they gain energy more often than they lose it. And then a very, very few particles, a very small number, are privileged to give them enormous wealth. And I won't pursue this economic analogy too far, but as we're working with the bank, but we'll say they're given enormous wealth and they have very high energies at the end of the process. How do they actually do this? Well, as I alluded to before, the thought is that there is a shock front in front of the expanding debris from the supernova explosion. And if you think about what happens at a shock front, is that I'm going to try and enact this here. If I imagine my hand here as being a shock front that's traveling into previously unsuspecting and unaware interstellar medium over on that side there. So the shock front is moving like that, across like this, and then the gas that's behind the shock front is actually following the shock front. It's going outwards, but it's falling behind the shock front as we move across like that, but it's still moving outwards. Now, the other ingredient that you need to understand is that there are magnetic fields and inhomogeneities on either side of that shock front. And those magnetic inhomogeneities allow charged particles, like protons and electrons, to be rebound from the gas on one side of the shock front there and the gas on the other side of the shock front here. And the magnetic fields are at rest in the gas on either side, and so what we have is scatterers here that are like that, and scatterers here that are moving like that. And so those two scatterers, or rebounders, these two reflectors or rebounders, are in fact approaching each other. And if we have a particle going 1,000 times, as it will do, backwards and forwards between them, they will gain energy, just like a game of tennis, where one player is essentially receding slowly from the net, and the other is going very fast into the net. And if it's an elastic tennis ball, the particle will go faster and faster as the two tennis players volley that ball between them. And this is a mechanism that we believe was postulated to accelerate cosmic rays. Its sort of spiritual origin was this famous Italian physicist Enrico Fermi, after whom the gamma ray telescope I started this talk telling you about was named. So this is a mechanism that appears to be happening, although there are still many details to be understood. Here is some of the astronomical evidence for this. This is the remnant, the expanding debris from a supernova explosion that was witnessed by Tycho Brahe, famous Dutch astronomer, in 1572, and it's been expanding ever since then. And you can see the blue X-ray light around the edges there. That marks the shock front, and that shows you where the electrons are radiating synchrotron radiation. Remember, there's this process, synchrotron radiation, which creates X-ray photons in this case. And so we can see the electrons, the results of the electrons gaining energy and then radiating away that energy by creating X-ray synchrotron radiation. And so this and many other sources like this are evidence that we have electron acceleration happening at shock fronts surrounding supernova remnants. Here's a more detailed X-ray study of the same source, Tycho's supernova remnant, and you can see all the little striations there. And that has told us something else very important about this process, is that not only do the supernova remnants accelerate the charged particles, they also amplify the magnetic field. So these shock fronts do two things. They accelerate charged particles, and they amplify magnetic field, which allows them to be much better at accelerating the particles and can accelerate them to very high energy. And this way we can accelerate the cosmic rays, as I said, up to energies about tens or hundreds of 10 to the 13 or 14 electron volts, shall we say. Now, that told us about the electrons being accelerating cosmic rays. In supernova remnants, most cosmic rays are protons, and the big challenge is to know where the protons came from. And the conjecture was that they were also accelerated by these shock fronts. And here is one piece of evidence out of several now that shows that this is almost certainly the correct explanation. The protons do the same sort of tennis match as the electrons, and they are scattered by magnetic fields. And what they do is, when this proton acceleration happens in dense regions, they create these particles which I mentioned called pions, which make gamma rays, and that has a rather distinct signature, and we have detected that signature now in several of these supernova remnants. And so we now seem to have a consistent answer to the question, a 100-year-old question: where do most of the galactic cosmic rays come from? And the answer is the majority of them seem to come from supernova explosions, and those supernova explosions have to convert about 10% of their energy into the cosmic ray protons so that they can make the fluxes that they see before they leave the galaxy. So this is a pretty exciting development that's really happened over the last five or so years. If we go on now to the highest energy cosmic rays, the ultra-high energy cosmic rays, here the story, and this is the evidence for this, is by no means as secure, and this is still very much a work in progress, but at least a very plausible explanation is the same sort of cosmic tennis goes on in much larger shock fronts that surround giant clusters of galaxies. So what we have is a giant cluster of about 1,000 galaxies way outside our galaxy. This one here is, in fact, the Perseus Cluster, and that you can see that is not a Halloween mask or a skull. That is actually X-ray emitting gas. And that is hot gas. And that hot gas has passed through a strong shock front. So these giant clusters of galaxies, their gravity pull is pulling in gas, passes through a strong shock front. Here's a simulation of the shock fronts on the right-hand side up there. And then we have now observations which show the properties of this gas and make it very clear that those shock fronts are every bit as strong, every bit as powerful as the shock fronts associated with supernova remnants, but they're up to 1 million times larger. And so, not surprisingly, they can accelerate particles to very much higher energies. In particular, they can accelerate the very highest energy cosmic rays that we've ever observed, provided that they are not protons, but heavier nuclei, like, for example, iron. So this is a less strong story at this point, but everyone is working on trying to see if it's right or wrong, and it's an interesting idea. And so it's at least a plausible explanation for the very highest energy cosmic rays. As we go on, I'd like to tell you now about a different type of particle acceleration. I've just explained the particle acceleration associated with shock fronts. Let me now tell you about a different type of particle acceleration, and I'm going to use the Crab Nebula as an example of something that is actually much more common. So you see that the Crab Nebula is varying, that those are time-lapse observations of the Crab Nebula, and it's changing and moving all the time. And what happens is it shines with a lot of power, and that power comes from the central spinning magnetized neutron star that we call the Crab Pulsar. And that Crab Pulsar has a 34 millisecond period, and I just tell you with a slight tear in my eye that when I first started doing astronomy, it had a 33 millisecond period, and so like me, it is slowing down. But it is now a 34 millisecond period, and it has a very strong magnetic field, 10 to the 13 times the magnetic field strength of the Earth. And it was observed by Chinese astronomers in AD 1054 AD. It was 6 times as bright as Venus on the sky, we believe. And it is now this expanding debris that's about 6 light years long. And what we see in this depiction here, if you look at the top image over there, you can see the blue image there. That is the X-ray emission from the Crab Nebula. It's X-ray synchrotron radiation. You can see a spot in the middle. Unfortunately, it doesn't come up. I'm not able to. I just see it there. That is the pulsar, just a tiny pulsar, as big as Madrid, no bigger than Madrid. And it powers the whole nebula, and what it does is it winds up magnetic fields and sends it out of the nebula, and then we can, and then that field accelerates particles, and how it does that is the big puzzle. Now so let me give you an explanation of how this is happening, and this is a fundamental principle of physics that was devised by Michael Faraday in the 1820s. And basically it was that if I have a conducting sphere, or disk in his case, and it is magnetic field around, and we spin it on its axis like that, then it will create a voltage. We can think about this as an electric field, or we can think about it more usefully perhaps as a voltage. And it's easy to calculate what that voltage will be. And in the case of the Crab Pulsar, where the neutron star conducts electricity very well, that voltage will be about 50 petavolts. So it's 50 petavolts, and what that means is 5 times 10 to the 16 volts. And so if I stuck an electron in that voltage, then what I would get is an energy of 50 peta-electron volts. You can see why we use this notation. We get an electron, or a proton would be the same. All right, so that's giving us energies up there, and what we see is that this energy, it also creates a current, and the current here is half a teramp. This is an awful lot of little batteries, an awful lot of flashlight batteries, if you like. So it's 5 times 10 to the 11 amps of current that's flowing through this. And the combination of those two is a giant electrical motor. And we can either think about it as magnetic fields, or we can think about it as currents flowing away from the pulsar here. See, I've blown that up, and these are white lines here are flows of current. We can think about it that way too. Either way, it's powering the nebula, and the question is, how is it doing that? Now, we got a very big clue about, just let me say what it actually does. This is a numerical simulation that is done by integrating the equations of electromagnetism and so on. And what happens, as you can see, is those field lines, which these lines here are lines of magnetic field like those around the Earth. When you keep on twisting them up like this and have them go out of the nebula, they get very tangled. They get twisted around, but they get horribly tangled too. And I didn't actually perform the true simulation doing that, but I did an analog simulation myself. In fact, I do it quite frequently. And you may have performed this one too, when you put all the computer cables in your pocket and then lift them out, then what you get is something like that, and you have to untangle them. So that is what I think is going on in the Crab Nebula. And let me give some evidence for that. Here is something we discovered using Fermi Gamma Ray Space Telescope. And this is that in the gamma ray range, the Crab Nebula flares dramatically about once every year, not regularly, but just about that frequency. And it creates energetic gamma rays. And in order to do that, this is again this trusty synchrotron radiation. The synchrotron radiation requires 5 peta-electron volts. That's 5 times 10 to the 15 electron volts, or requiring 10% of the voltage that the Crab Pulsar is creating. And it produces this variation here. Unfortunately, I'm not showing it here. Those are variations on timescales of several hours. So we've got a nebula that is light years across, and it is able to create particle acceleration and gamma ray emission by the synchrotron process on timescales of several hours when it's many light years across. So something inside it, not the pulsar, we know that, something inside it has got to be able to do this dramatic particle acceleration. And what we think might be going on is that it's one of these untangling events of these tangled magnetic fields like my cables here. And so this is sort of like a little metaphor. This is, if you think about these magnetic fields as being like ropes, and that is a slip knot, of course, and you can imagine that simplifying. There are other processes at work, but this is the one that will make dramatic particle acceleration. Imagine replacing that by a magnetic field, some sort of reorganization like that as we just perform the untangling of the field lines, that can create dramatic particle acceleration. So that is and so this constant untangling and simplifying of the magnetic field, which must happen in the Crab Nebula, and indeed in many, many other sources, is responsible for these very dramatic particle acceleration and emission events, these flares that we see. That is the conjecture. So far, I've just talked about neutron stars, not talked about black holes. Let's see what the part of the story they have. Oh, there we are. Okay, I forgot to advertise the name that we give to this process. It's a fancy name. We call it magnetoluminescence. So when you simplify the magnetic fields and untangle them, and they make giant sparks, then we call that magnetoluminescence. I meant to say that. Okay, so let's talk now about black holes. Everybody seems to know about black holes, at least from the movies, and also, I think, from science. And basically, the idea is when matter gets so concentrated, it can create a region, a surface, if you like, called the event horizon, from which nothing can escape, not even movie stars, let alone for particles of light called photons. And if the sun were to do this, then the size of the black hole would be even smaller than the neutron star, about 3 kilometers. In fact, the black holes we know about are a little bit more massive than that, but the thing about them that's remarkable is that they are elementary particles in a way, and that they're really, as far as astrophysics is concerned, just characterized by their mass and their spin. And they can do exactly the same trick as the neutron stars do. If they're spinning and there's magnetic field around, then they can create enormous voltages. And those voltages can, in principle, in some types of black holes, accelerate the highest energy cosmic rays. Now, what we have here on the right-hand side is a numerical simulation of those black holes creating creating large voltages and currents and magnetic fields. The magnetic field lines are shown in black there. And what you can see is something we discovered from these simulations is a sort of hula hoop type action there. And so we've got a flow up and down like that, a flow up and down of magnetic energy, electromagnetic energy going up and down, and we also have a sort of twisting around of that motion, and that twisting around is being sought but hasn't yet been seen. But these outflows of energy in concentrated columns, if you like, up and down, they are called jets, and we have known many examples of those. We've seen them many times, and I'll show you some observational examples in a moment. So let's tell you about what we know about black holes. We know that they are formed in supernova explosions with masses something like about 10 to perhaps 30 or 50 times the mass of the sun. And here's one that we believe made a black hole. This was a supernova explosion, which many of you may recall, that happened in the Large Magellanic Cloud in January 1987. And this is what it looks like now. This is a sort of imaged enhanced three-ring circus, if you like, that has, but this is the expanding debris, and most of us believe that the central object left behind was a black hole. We see them very commonly, we think. We're not totally sure about this. This is still an advanced conjecture, if you like. We see them in gamma ray bursts. These are objects that are seen across the universe. And those gamma ray bursts happen, we observe them about once a day, and we think they are the birth cries of black holes, either formed inside supernova explosions in a small minority of cases, or else formed when we've got two neutron stars which lose energy through gravitational radiation and collapse together. So those are the two explanations. So that's a picture of a gamma ray burst, and this is a picture of the distribution in fact, it's the durations of the burst. They only last for seconds, and the ones that are short are believed to be neutron star mergers, and the ones that are long are believed to be produced in a special type of supernova explosion, and those are the gamma ray bursts. And we can also observe these black holes, and this is how they were first discovered, when they are mature objects and have companion stars that are giving them gas. Okay, so those are the black holes, if you like, that are associated with stars that have masses between, say, a few times the mass of the sun to maybe 30 or 50 times the mass of the sun. There are also massive black holes in the nuclei of galaxies. So most normal galaxies appear to have massive black holes in their nuclei with masses that range from 1 million times the mass of the sun to 10 to the 10 times the mass of the sun. So we go up to 10 to the 10 times the mass of the sun. I'm afraid I used the ambiguous billion here. And one of them close by, which I'll come back to in a moment, has a mass of 7 times 10 to the 9 to the mass of the sun. What you can see here are the orbits of stars around a rather special black hole. It's the black hole at the center of our galaxy. There is a black hole at the center of our galaxy, and beautiful infrared observations made using the Keck Observatory in the very large VLT in Chile, European telescope. Both of those have monitored the motions of stars around that black hole, just like planets orbiting the sun. And so by following the stars around that black hole, we can get an accurate mass of the black hole and demonstrate beyond all reasonable doubt that it really is a black hole. And as I say, this is a very small black hole. This one, it's only about 4 million times the mass of the sun. but don't be, when it's a very big black hole, we'd call it a quasar, and it would be outshine the galaxy. Don't be sad that our black hole is rather small and insignificant. You wouldn't want to live next to a quasar. So the environmental impact is nothing special. So these black holes, they make jets, as I mentioned. So here is M87, that's the one that I mentioned. So if we go inward bound, we look on the largest scale, it's in a cluster of galaxies, of which I mentioned one. And then as we go, there's a giant galaxy at the center of that cluster of galaxies, that's M87. Then if we look in there with Hubble Space Telescope, we can see one of these jets that squirts out of the black hole. If we go on to smaller scales, using Chandra X-ray Observatory, we see the same jet there, and we then use the very large array, which I showed you a picture of. There's the radio image, and we see this one-sided jet. In fact, there's another jet on the other side, which we can see. It's just not shown up very well here. And then if we look on even smaller scales at radio wavelengths, we see that. And then on the smallest scale on which we can currently make an image, it is about 100 times the so-called Schwarzschild radius, the size of the event horizon of the black hole. We are making images on the scale of about 100 times the size of the black hole. And in fact, we're seeing structure on the scale of about 10 times that. Here's the reference to that. So about 10 times the size of the black hole, we are seeing structure, but we don't have enough resolution to make a good image, but we're getting there, and that's the hope. We will be doing that in the future. So this is a 7 billion solar mass black hole, and it's about the same angular size as the black hole we have at our galactic center, which of course is much closer. And both of those are objects of study in the future. Just let me show you a few more of these jets made by the black holes in galactic nuclei. And here is a famous one called Cygnus A. This was one of the first radio sources ever discovered, and you can see the jet there. Unfortunately, just there, you can just see it there, that's right, coming out from the center of the galaxy where the black hole resides and inflating these giant lobes of radio emission made again by the synchrotron radiation process. It's radio waves that they're making, but they also make X-rays. Here's another one, a dead straight jet that comes from the black hole, which is there, going all the way outside the galaxy in a straight line. This delineates this channel that's created by the black hole and piles out into the intergalactic medium. Here's another one there. Sometimes they can be made to dance around. Here's one where they come in pairs and so on. So we know a lot about these jets, and it's been a puzzle for a long time how they were created, but it now appears that they're created by the spin of the black hole itself through these magnetic fields. So this is the first quasar that was discovered, 3C273. There's its jet there, and what we see is that we can see features moving there, expanding, with material moving very close to the speed of light, though it appears to move faster than the speed of light. And again, the particle acceleration in these sources is dramatic, just in the same way as it is dramatic in the Crab Nebula. We see emission varying, in the case of 3C273, on timescales of about half a day, just like the Crab Nebula, but in a region that's many, many light years across. It's the same phenomenon. We have this very dramatic variation in a very large region, and it probably requires a rather similar untangling mechanism of those magnetic fields that are created by the central black hole. Here's something even more dramatic, and this was an observation by the MAGIC telescope in La Palma, the one you say this is one of many major discoveries that it has made, and this is observations not seen at GeV energies at 10 to the 9 electron volts by Fermi, but at 10 to the 12 electron volts by a ground-based Cherenkov telescope, like the MAGIC telescope. And look at this. This one varies in 10 minutes. And there's another one that varies in 2 minutes, and yet it has to come from a very large and extended region. So the same phenomenon that we're seeing in the Crab Nebula, we're seeing in these quasar jets, or AGN jets we should call them, and we also see the same sort of thing happening in the gamma-ray bursts. So this is all very exciting. What I've shown you has been based on numerical simulations and physics conjecture. There's nothing to beat an observation, and I alluded to the fact that we're getting better and better at looking in at the black hole, and this is where where we hope to be going in the next 5 years or so, using the ALMA millimeter and submillimeter telescope in Chile in combination with other similar telescopes distributed around the Earth. We can use them as one giant telescope, and we use them as a giant telescope to get incredibly fine resolution. It's called the Event Horizon Telescope, and the aspiration is to make an image of the gas and the electromagnetic fields and the radio waves, the millimeter waves, excuse me, from right around the black hole, to start making an image. So we don't have to rely on Hollywood to say what it will look like. We can actually get some astronomical observations. And this is, I say, what we've done so far is about 100 times that, but we're starting to see the structure on 10 times the size of the black hole. And this is what numerical simulations say we should see. And it would be very exciting to see if the numerical simulations are anything like what the observational astronomers see with their radio telescopes. So I think my time is more or less up now. I've tried in this talk just to give you a flavor of the wonderful range of particle acceleration that is possible in the cosmos. That nature has invented all these mechanisms, and we're struggling to catch up to try and see how it does it. And here's, if you like, a summary. It's the same summary I showed before, but I've given a few of the examples here. And so this huge range of particles for energies from individual particles of electron volts all the way up to 10 to the 21 times that. I believe that there are just a few small processes that are responsible for most of this, although there is much subtlety and individual differentiation. And probably the two most important are acceleration at shock fronts and also the creating of giant voltages by spinning magnetized bodies, which can then spark, or equivalently, we can say, untangle magnetic fields in a dramatic and sudden way. Those two mechanisms, I suspect, are responsible for much of what we see, but the proof will come in future observations, and the future in this business and much else in astronomy, astrophysics, and especially cosmology, remains very bright. Thank you for your attention and your invitation here.